This is a response video to Jeranism's Please Explain It to Me Volume 1, Earth, Sun, and Moon Connection. The link to his original video is provided below. I'll walk through the questions and attempt to make the explanations clear without showing any math. Okay, I'll start with his first question, which I believe he posed rhetorically to set up for the moon question that follows, but I'll address it anyway. To paraphrase his first question, big rock, little marble. Would the marble fall down toward the Earth? First off, a rock 5 miles in diameter couldn't sit on the Earth as he shows. Rock isn't strong enough, it would collapse under its own weight into a heap. But let's pretend it wouldn't for the purpose of this thought experiment. The answer is, of course, that yes, the marble would fall down toward the Earth, but not in a perfectly straight line. The big rock would also have a small gravitational effect and would pull the marble slightly toward it as it fell. So the marble would follow a slightly curved path and land a little closer to the big rock than it would have if the rock weren't there. If you ignore any other interfering forces like updrafts and air resistance, you can work out by how much the path would be curved using Newton's universal law of gravitation once you decide on the mass of the rock, the marble, and the distance between the two. On to your second question. To paraphrase this two-part question, part 1, when the moon is new, that is, when it is between the Earth and the Sun, wouldn't the Sun's greater gravitational pull yank the moon out of Earth's orbit? And part 2, does the moon get faster in its orbit as it approaches the Sun and slower as it moves away? Well, to begin with, you have it in reverse. When the moon is new, that is, when it's between the Earth and the Sun, it is pulled toward the Sun by the Sun's gravity, but it is also pulled in the other direction by the Earth's gravity, so it feels the Sun's pull the least at that point. When the moon is full and the Earth is between the moon and the Sun, the moon feels the pull of both the Sun and the Earth's gravity in the same direction, so it feels the greatest pull toward the Sun at that point. The moon is indeed nearest to the Sun at new moon and furthest away at full moon. But the difference between nearest and furthest is not very large, only about half of 1% of the total distance to the Sun. The Sun is 400 times further away from the moon than the Earth is, but it's far more massive, so it indeed does have a greater gravitational force on the moon than the Earth does, about twice as great, in fact. But the moon is in what is called Earth's Hill sphere, named after astronomer George William Hill, who worked out the math for this. By the way, there's also a crater on the moon named after him. He showed that if a satellite, either a natural one like the moon or an artificial one, has an orbit that lies within a planet's Hill sphere, it will be retained by that planet instead of being pulled away by a neighboring body. In other words, the moon is gravitationally bound to the Earth. The Earth's Hill sphere relative to the Sun extends out to about 930,000 miles, and the moon's orbit is about 235,000 miles, which is well within that radius, and therefore the moon remains in orbit around the Earth and is not at any risk of being pulled away by the Sun. As an interesting side note, if we moved the Earth and the moon to an orbit of about 23 million miles from the Sun or closer, the Earth's Hill sphere relative to the Sun would be much smaller, and the moon would indeed be pulled away into an independent orbit of the Sun. Looked at from another perspective, the Sun has already captured the moon. The moon is in orbit around the Sun, or rather the Earth-Moon system is in orbit around the Sun. If the Earth suddenly disappeared, the moon would continue orbiting the Sun on its own. The Earth and Moon are in orbit of each other, with the center point of that orbit being on the line between their two centers at a point called the barycenter. If two orbiting bodies have the same mass, their barycenter is at a point directly between them. In the case of the Earth-Moon system, the Earth is far more massive, so the barycenter is closer to the center of the Earth, about 1,000 miles below the Earth's surface. The Earth and the Moon do a kind of dance with each other as they travel around the Sun, perturbing each other's orbit around the Sun as they go. So the Sun does pull on the Moon, but it pulls on the Earth at the same time. The net effect is to keep the Earth-Moon system in orbit around the Sun. The perturbations in the Moon's orbit caused by the Sun's gravity can be worked out, and that math is part of the calculation used to determine the exact location of the Moon at any point in time. Question 3. To paraphrase this question, why does the Moon cast the shadow it does on the Earth during an eclipse instead of a much larger one? He then goes on to describe a setup with a basketball for the Earth, a baseball for the Moon, and a flashlight acting as the Sun, and wonders why the shadow isn't much larger on the Moon than it actually is during a solar eclipse. His thought experiment with the balls and the flashlight would indeed give the result he suggests. But a flashlight is neither large enough nor far enough away to simulate the Sun, and that makes all the difference. The Sun from Earth looks like a disk of light, almost exactly the same size as the Moon in the Earth's sky, about a half a degree of apparent size. It is also nearly 93 million miles away. To simulate the Sun in his model, he'd need a light source 107 feet across and 11,532 feet away from the basketball Earth, with his baseball Moon about 30 feet out from the basketball. Imagine that you're viewing a total eclipse of the Sun at the peak moment. It would look like this. If you were stationed 100 miles away in any direction on Earth at the same moment, from your vantage point you'd see part of the Sun again, much as if you were at the movies and shifted your head to see around somebody sitting in front of you. If you were stationed 500 miles away, you'd see even more of the Sun. The eclipse would be partial for those locations rather than total. If you were stationed more than about 2,200 miles away in any direction on the ground, you would see the entire Sun, and there would be no eclipse at all. For the location that sees a total eclipse, the shadow cast by the Moon is darkest at that point. For watchers further away seeing only a partial eclipse, the shadow is lighter and lighter depending on how much of the Sun is visible from their locations, which in turn depends on how far away they are from the total eclipse location. In technical terms, the darkest part of a shadow is called the umbra, and the lighter and fuzzier outside part is called the penumbra. If the Sun were a point source of light, there'd only be an umbra, a sharp dark shadow with no fuzzy edge. In other words, the Moon would block either the entire Sun or none of it from any given viewing location with no shades of gray in between. But the Sun isn't a point source of light, so there's also a penumbra, and the size of that penumbra relative to the umbra is a function of the distance of the Moon from the Earth. Here's an animation to demonstrate that. I've modeled it with accurate relative dimensions. If the Moon were touching the Earth, as I've shown here in the first frame, it would have a shadow directly beneath it. That was all umbra with almost no penumbra. Now, if we begin the animation, the only change in these successive frames is the distance of the Moon from the Earth. As we move the Moon out to where it actually orbits, you see the umbra shrinks and the penumbra grows in size and brightness. This matches up with an actual photo of an eclipse shadow as seen from space. Anyhow, I hope this has helped answer these questions. If you've liked this video, please give it a thumbs up. If you'd like to see more videos like this, please hit subscribe and leave comments below if you have any. Thank you kindly.